Hi everyone. So in this video we have this question about the magnetic field. Okay, so this question was given to me by one of my students. Okay, so now the argument here, that's we have two questions actually, but the argument here is that um, the magnetic field, the magnetic field of a straight wire carrying conductor and that of a circular coil, okay, can be measured differently. Okay, and I already explained the proof. Okay, I already gave him the proof as to how to measure the magnetic field intensity for a straight wire carrying conductor and that of a circular coil. Now, now let's find out what is the magnitude of the magnetic field at a point 50 millimeters from a wire carrying current of 30 amperes. Okay, which is the first question. Now the second question is, we have a circular coil, okay, of radius 40 millimeters, consists of 250 tons of wire, okay, in which the current is 20 amperes. Okay, so we want to know the magnitude of the magnetic field in the center of the coil. Okay, now for the first question, we have Now, for the first question we want to calculate the magnetic field at a point 50 millimeters from a wire carrying current. So, which means we know that for a straight conductor carrying current, the magnetic field, okay? All right, so let's talk about a straight conductor carrying current. Now, this is a straight conductor. This is a straight conductor. Okay, we have a straight conductor. Now, let's say we have this placed on. Okay, we have the conductor, we have a straight conductor, and we have the lines of the magnetic field. This is the lines of the magnetic field. Lines of the magnetic field. Now, we have the direction of the current. So the current is entering the straight conductor. Okay, the current is entering the straight conductor. Now we know that according to the right hand screw rule, okay, we know that if a right hand screw, okay, advances in the direction of current, then the direction of rotation of the screw, okay, will be in the direction of magnetic field. So we can apply that in this case. Now we can also apply the that's the magnet. That we can also apply the one we call the right hand grip rule. So in the case of right hand grip rule, when we grasp a wire or a straight conductor carrying current, okay, and we use the thumb, and the thumb finger, okay, is placed along the conductor and it is pointing in the direction of electric current, then the direction of rotation, or the direction of the coiled finger, okay, will be represented using this line. You can see that we have these concentric circles around the straight conductor carrying current. Okay, so which means as current pass through the conductor, the straight conductor, okay, now the what's it called, like in the case of that of compass needle, we notice that the compass needle will swing around the straight conductor, and then now point in a certain it will now point in a certain direction, telling us the site of magnetism. Okay, so to now measure the magnetic field intensity in this case, now the magnetic field intensity, the formula is we have B equals to permeability of free space multiplied by I divided by 2 by R. Okay, where we have this guy, okay, to be called permeability of free space. This is called permeability of free space. Now the magnitude of permeability of free space is the 4 pi times 10 raised to the power of minus 7 Tesla per meter. Okay, now so we're also giving the current, okay, the current. So we're giving the magnitude of the current to be 3 amperes. In this case, that's the current entering the straight conductor. Okay, so we have the magnetic field, okay, to be B. Then we also have the magnetic, that's the permeability of free space. So in this case, so we have our B to be equals to 4 pi times 10 raised to the power of minus 7, okay, multiplied by 3, which is the current, okay, that's the current entering the conductor. That's the current entering the conductor. Don't forget, that's the formula for the magnetic field of a straight wire carrying current. Okay, so we are going to divide it by 2 pi, then we multiply by the radius. Now, also we are given the radius is given to be 50 millimeters. Okay, 50 millimeters, and that will be 0.05. That will be 0.05. When we divide 50 by 1000, that will be 0.05. So this is going to be 2 pi, okay, 4 pi divided by 2 pi, that will be 2. So 2 multiplied by 3, that will be 6. Then we multiply by 10 raised to the power of 7. Then we can write 0.05, okay, in what we call standard scientific notation as 5 times 10 raised to the power of what? Negative 2. Now the unit of B is the what? Tesla. So we have B equals to, we know that 6 divided by 5. 6 divided by 5 will be 1 point, that will be 1.2. Yeah. Yeah, that will be 1.2 times 10 raised to the power of minus 7. Now we have to bring this guy up. That becomes plus 2. So the unit is what? Tesla. So that B will be equals to 1.2 times 10 raised to the negative 7 plus 2. That will be negative 5. Then Tesla. So which means the magnetic field intensity is 1.2 times 10 raised to the power of minus 5 Tesla. So this is the magnetic field of a straight wire carrying currents. Magnetic field of a straight wire carrying currents. All right, so the second question, we have a circular coil of radius 40 millimeters, consists of 250 tons of wire, in which the current is 20 milliamperes. So which means we have the radius, okay, the radius is 40 millimeters, and that would be, we have R to be 0.04 meters. Then also we are given the number of tons. Okay, we are given the number of tons. Number of tons, that's N. That will be 250. That's 250. Okay, then we're also given the current. So the current entering the conductor, which is the circular coil, that is given to be 20 milliamp, and that will be 20 times 10 raised to the power of negative 3 amperes. All right. Okay, so what is now the formula for calculating the magnetic field of a circular coil? Now, for a circular coil, let's say we have this. Okay, this is when we talk about a circular coil. Okay, the field lines, the coil is entering, then coming out this way. Okay, so we have the direction of the currents, then the lines of induction of the magnetic field. That's the line of induction of the magnetic field. Yeah, so the magnetic field of a circular coil will be equals to, now remember this time we, for this one we have number of turns or number of wraps or number of laps of the what? Of the coil. So we have the permeability of free space multiplied by the number of turns multiplied by current I divided by what? 2R. So this is the magnetic field of a circular coil. Okay, for this one we have magnetic field. Remember, this is magnetic field of a straight conductor or wire, okay, carrying current. So this is the magnetic field. This is the magnetic field of a circular coil. okay, of a circular coil, which is different from that of solenoid, okay? Because somebody was asking me, is this not the same as the magnetic field of a solenoid? So for a solenoid, it will be N, that's permeability of free space multiplied by number of turns multiplied by current I, the all over what? L. That is the length of the straight conductor, or the length of the, a solenoid is a long cylindrical coil, okay, which becomes a magnet when current is passed through it. So that's a solenoid. So in this case, so we have, so we're going to plug in the value. So we have B to be equals to 4 pi times 10 raised to the power of minus 7, because we know that permeability of free space is 4 pi times 10 raised to the power of what? Minus 7. So we then multiply by the number of turns, 250, then multiply by the current, which is 20 times 10 raised to the power of minus 3, all over 2 times the radius. Yeah, the radius is 0.04. We can write that to be 10 raised, that's 4 times 10 raised to the power of minus 2. Yeah, so this, we cancel this, okay? Now, 2 out of 20, that will be 10. We know that pi is what? Pi is 3.14. So we have 3.14 times 10 raised to the power of minus 7 multiplied by 250 times this 10 multiplied by 10 raised to the power of minus 3. So let's make this guy come here. So it will become plus 2. It becomes plus 2. So now let's get the value for 3 point, what is 3.14 multiplied by 250? Okay, that will be 785. That's going to be 785. Okay, so we have 785 multiplied by 10 raised to the power of negative 7. Okay, then multiply by 10 raised to the power of 1, multiply by 10 raised to the power of negative 1. So this is going to be, um, 10. Now 10 raised to the power of 1 minus 1, that will be 0. So we then have 7.85 times 10 raised to the power of negative 5 Tesla. So this is the magnetic field of, that's a magnetic field in the center of the coil. This is the magnetic field in the center of the coil. So remember, the magnetic field of a circular coil is a permeability of free space multiplied by number of turns and the current, entering the coil, all divided by 2R. But for a straight wire carrying current, then it is permeability of free space multiplied by current, all divided by 2 pi R. Bye-bye. Thank you.